So here is my boat. On the left we have a little debug thing which will tell us the current acceleration of the boat. When we hit W, the boat will begin to accelerate. As you can see, the velocity is slowly increasing. It's reached the maximum velocity possible with this acceleration. Increase it again, accelerates a bit and has reached the maximum velocity. We can accelerate further and increase higher velocities. We can decrease acceleration and go to lower velocities. We can also rotate and turn around this buoy at the end of the path. As you can see there's a little bit of drift as the movement in one direction slowly changes. Let's see if we can go faster and show this off a little bit more. So as we see, we're drifting in the X direction. There we go. And there's some simple things about the game. Now let's look at the code. So this is the header file for our boat class. The boat class being the class that deals with all the things for the boat. We have the first three vectors: acceleration, velocity, and displacement. These are fairly self-explanatory. We have the heading vector. This just tells us the direction in which the boat is looking and the direction that it should accelerate in. Camera location and rotation. Camera location tells us what the camera is, and camera rotation tells us where the camera is in relation to the boat, as in, like, we use this to rotate it around the boat. Now if we look at the code for the boat itself, when we start we set several of the variables. This here makes sure that the camera is behind the boat, 7 units above it in the Y direction and 15 units behind it in the Z direction. Make sure all the displacement, velocity and acceleration is all 0. We start off with the 1 in the Z for the heading, just to say that we're looking in the Z direction. And we also set the camera rotation to the camera location. This means that when we calculate the camera rotating, it is always relative to the camera location. Now if we look at the functions for increasing and decreasing acceleration, when these are called, it simply increases the acceleration by a uniform amount. Now looking at the left and right rotation functions, we increase rotation by a small increment. We rotate the heading around the y-axis by the same increment. So this will tell us later, when we implement the heading with the velocity, which way the boat is moving. And the camera rotation will rotate the camera around the y-axis by the same increment, so it will face the same way as the boat. The turning function simply limits the rotation variable between 360 and negative 360 degrees. The motion function is where the majority of the physics happens. So firstly we make sure that the acceleration doesn't go too high. It's worth noting that the X and Z acceleration increase at the same amount. This is because when we multiply the acceleration by the heading is effectively a percentage that we use multiplied with the acceleration to tell us how much of the acceleration we should use for each direction. So when we rotate the heading starting off with just 1 in the Y and 0 in the X. When we rotate around with the Y direction, the Z will go down as the X goes up, and vice versa. So this is then multiplied by the acceleration. So if we're facing in one direction, and purely in one direction, not facing in any other direction, you will accelerate only in that direction. If we face and start to turn, we will accelerate in whichever way we are facing. This next part of the code emulates drag. The first thing we do is we take the velocity and multiply it by a small number so that it's only a part of the velocity. We then take this away from the current velocity. So this means that if we are moving, then we will slowly slow down and come to a stop. If there is acceleration, then the acceleration and the negative velocity will eventually balance out, giving us a natural maximum speed. This also means that if there is no acceleration, we will come to the stop. And most notably is that if we are turning and turn in a direction so that we say we're moving the X direction, we turn to face the Z direction, our movement in the X direction will slowly come to a stop, so the boat will drift, but it will not go too far in the wrong direction. We also have a hard cap on the maximum velocity. This doesn't really come into play though, as the drag gives it a natural maximum speed. After this, we add the displacement to the velocity to give us the new displacement. This is where delta time would be if it was implemented. That effectively means that the boat would move at the same speed, and the hardware you're playing it on would not make a difference. However, at the moment, the faster the frame rate, the faster the boat will move. Then we just keep the camera location so that the camera stays behind the boat at all times and moves with the boat. When we draw the boat, we use push and pop matrices. This push matrix means that we take a copy of the current location of everything that we've drawn in the scene so far. So we then move where we want to draw the boat by the displacement of the boat, so that we draw the boat where it should be. And similar with the rotation, we rotate the boat so it's the correct rotation. We then draw the boat, or draw this part of the boat, as the case may be, and then pop the matrix, which means we return everything to where it was when we push the matrix. So everything will move back to where it was, but the boat will stay where it is, so that it is in the correct position relative to the rest of the scene. When we draw the two parts of the prow, we also move those. When we draw the prow, we move them slightly in the X direction, so they appear on either side of the prow of the ship. Now, in the main bulk of the code, we create a object of the class boat. This would be the player. As we draw the scene, we have the camera move to the camera location, which is set in the boat class. This function here is what actually moves the camera. So it moves the camera with the boat, and it will continue to look at the center of the boat. Here we draw the sea. It is good to note that whenever you draw something, just be safe. If you're doing any kind of movement, you can use the push and pop matrices either side of the drawing. After that, after we've drawn the sea, we then draw the boat. We then create a buoy, and we use this function here to create a line of them, one on either side, and one all the way at the end that we use to turn around. Here we have our implementation of the keys. So if we hit W, we increase acceleration, and S will decrease, A and D rotate left and right. And this is the main game loop, which we set as the idle function down here. This will call on every update. So we make sure that the player turns correctly, and then we make sure that the player moves correctly. This ensures that the boat moves correctly, and this will then redraw the scene so that we see what's currently happening in the code, or we will see the correct drawing of the scene. I would like to briefly talk about the axes in OpenGL. So OpenGL uses the right-handed rule, which means that if you stick your thumb out, your index finger out perpendicular, and your middle finger perpendicular to both of those, you get an idea of where the axes are in OpenGL. So firstly, your thumb is the X direction, your index finger is the Y direction, and your middle finger is the Z direction. This normally means that X is to the right, Y is up, and Z is towards you. However, in my game, I've rotated this 180 degrees so that Z is away from you, Y is still up, and X is to the left as opposed to the right. Now, if we look at the acceleration graph, as we increase the increments, when we press a button, apologies for the shoddy drawings, the acceleration will just increase, and we'll go up to 5 and decrease in the same way. There won't be any smooth curves. It will just be straight to the next level. Velocity, however, as we increase acceleration, the velocity will increase linearly. If we increase acceleration, it will curve upwards. As we reach the maximum velocity, it will plateau. If there is no acceleration, the velocity will slowly decrease due to the drag, and negative acceleration will cause it to decrease faster. One thing to note is there is constant acceleration in the beginning, and as opposed to having a constant line, there will be a slight curve due to the drag.